Welcome to the lecture 18 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, we will describe origin of series and shunt resistances in a solar cell and then equivalent circuit for solar cell. In last class, we have solved the diffusion equation and finally we got the expression for photocurrent. Also, we discussed IV characteristics of a solar cell and some performance metrics of solar cell, for example, fill factor, power conversion efficiency, etc. In this lecture, we will focus on series and shunt resistance. These are the resistances faced by a solar cell in practical structure. And then we will discuss effect of these resistances on the performance of solar cell, and the equivalent circuit including the series and shunt resistances will be discussed. Equivalent circuit for an ideal case, ideal solar cell, that is if we don't consider any loss due to presence of series and shunt resistance, this can be expressed as a combination of a current source and a dark current source ID, because the expression in the last class we have derived, that is I, the current, is nothing but IL. In last class, the expression for current we discussed, the current in a solar cell is IL, that is a photocurrent, minus I0 exponential QV by KT minus 1. This is the diode current part. So this equation can be represented in the form of a equivalent circuit, and if we construct the equivalent circuit in this way, here the current source represents the photocurrent IL and ID is a dark current, and you see ID direction and IL direction are opposite. The net current I will be IL minus ID and the terminal voltage is V. If you consider the diode current direction as a reference positive direction, then IL will be negative of that. But here we have considered IL positive and diode current is opposite to that. That is, the negative sign is appearing in the diode current part. Because in this figure it is clear that the photo-generated electron hole flow and dark electron hole flow are in opposite direction. This we have already discussed in detail in last class. So this portion is called ID and this is photocurrent. However, in a practical solar cell, some losses are there due to resistance of the quasi-neutral part, resistance of the contacts at the two ends, because semiconductor has a specific resistivity, and when photocurrent passing through the quasi-neutral region, it exhibits or it exerts some resistances. Similarly, there may be non-ideality in the formation of p-n junction, and due to that there may be formation of path, that is called bypass path, to flow the current, and that contributes to the leakage current. Due to that leakage current also photocurrent is reduced. So these effects can be included by two resistances, One is called series resistance, another is called shunt resistance. What I mentioned that conductivity of a semiconductor is governed by this equation sigma, that is the conductivity, that is equal to Q n mu n plus P mu P. This is general expression. N is carrier concentration of electron, mu n is the mobility of electron, P is the hole concentration and mu P is the hole mobility. This summation multiplied by Q gives you the conductivity. If the semiconductor is extrinsic type, that is if it is n type more than concentration of hole, in that case you can neglect the second term. Only Q n mu n will be the conductivity. Similarly, for p-type semiconductor, you can neglect n term corresponding compared to the hole concentration P. In that case, only the second term will exist. But for intrinsic semiconductor, contribution of the both terms will be almost equal. The resistivity, that is just inverse of conductivity, that will be Q into n mu n plus P mu P inverse. So due to a specific resistivity of the semiconductor material, particularly in the quasi-neutral region, there is a resistance. That resistance is called series resistance. So let us discuss the origin of series resistance, and then we will discuss origin of shunt resistance. The resistance of the semiconductor material, which is governed by this rho resistivity, and resistivity is rho, so resistance R is equal to rho L by A. That formula can be applied to calculate the resistance of the quasi-neutral part. Also, there are some resistance offered by metal and semiconductor contacts. We discussed metal semiconductor contacts. They may be ohmic junction, there may be Schottky junction. However, a resistance is offered in metal semiconductor junction, and that resistance also need to be included for the accurate modeling. Resistance of the interconnections between cells. In case of modules, actually this is important, because in a module, you know, there are array of solar cells. Say n number of solar cells are connected in a series, and such connected n number of cells are again parallelly connected with m rows. So there may be m by n number of solar cells. So interconnection from one cell to another cell, that interconnection is generally made by a connecting wires, copper wires or whatever may be. In that case, the resistance offered by that interconnection also contribute to the series resistance in case of module. Resistance in the wiring and soldering points, because when you make connection to form a module, one cell to another cell, you have to solder externally by a connecting wire. So soldering also gives you some resistances. So these are the main origin of series resistances. All these resistances, after taking into consideration the term RS, the series resistance will appear in the equivalent circuit as well as in the equation. Now let us consider the origin of shunt resistance. Shunt, by this meaning, there is a bypass path. So in the figure, we see that the flow of photogenerated carriers and flow of dark carriers both are crossing the PN junction. And if in the PN junction there is some bypass, that is a short resistive path, then the physics whatever we have discussed for carrier motion, that is under drift, under diffusion, that may be violated in that case, that in that path, and current may follow some low resistive path in the junction. So this is mainly occurred due to non-idealities or some imperfection in the junction. Maybe some pinholes in the junction, maybe some defects in the junction. And due to this bypass path, the current which is passing through that bypass path will not contribute to the photocurrent. That's why it's called leakage current. So shunt resistance is modeled to include the effect of these leakage currents. And these shunt resistance may be due to manufacturing defects like impurities or crystal defects, particularly at the junction point, damage to the junction during fabrication, because solar cell fabrication process, there are some high temperature processes, some other processes that may damage the surface of a P layer when you are making, say, N-type layer by diffusion process or by ion implantation process, that the formation of PN junction also we discussed. So during that period, surface of a P region may be damaged. That means basically in the junction between P and N, there will be some damaged, and defects obviously is the result of this damage, and due to these defects also there are some leakage current. Poor edge isolation, also this is another leakage path. Whenever you are making layer after layer to form a PN junction solar cell, so the edge of bottom layer, if it is sorted to the edge of the top layer, then instead of flowing the current through PN junction, it may flow through the edge, because edge are sorted. So proper edge isolation are required. This is the part of fabrication process. So due to imperfect edge isolation, current may leak through the edge of the top layer to the edge of the bottom layer, or vice versa. In that case, that leak current will not contribute to the photocurrent. So that is also cause of a shunt resistance. And all these effect is included in the model by putting a resistance, shunt resistance, and this resistance must be in parallel to the original current, because this current is leakage current. So let us now discuss the modification to include these effects in the solar cell characteristics and also the equivalent circuit. When the photocurrent flows through these resistive elements, suppose Rs, then across this resistance there will be a potential drop. Obviously, because Ohm's law tells that V is equal to I into R. So whenever the photocurrent is passing through the quasi-neutral region and resistance offered by this quasi-neutral region, say Rs, so some potential drop I into Rs, IL into Rs will drop across that resistance. So this potential drop will be loss. So this will reduce the terminal voltage. So this also reduces the fill factor. Fill factor, as it reduces the terminal voltage, so power of the solar cell also will be reduced. And ultimately we will show you it causes the effect of fill factor, that is fill factor is reduced and efficiency also to drop. And it mainly affects the slope of the IV curve near the open circuit voltage. Say this is the IV or here JV curve, the similar thing, I and J is the current density and I is current. This is the current density versus voltage plot. In ideal case, that is if there is no series resistance, say blue, this curve is there. That means it perfectly, almost perfect. There is no change in the corner voltages current characteristics. Or you can say the value of Rs in case of this blue line, it is very less, and this is 0 ohm centimeter square. The RS value is, unit is ohm centimeter square. 0 means no series resistance. Now if you have some series resistance, that is, if you include some series resistance in the model or in plot of IV curve, say 10 ohm centimeter square RS is included, you can get a red dash line curve. What it indicates? It indicates the corner is coming towards the origin. Similarly, for higher value of RS, further decrement in the corner things are there. And near the open circuit voltage, this slope is changing, and the is RS will affect mainly the slope near the open circuit voltage. Also, it can be calculated from the slope near the open circuit voltage. That means if you have a practical IV characteristics or experimental value of IV characteristics of a solar cell, from that characteristics, by taking the slope, also you can calculate the value of RS. And due to this change in the IV characteristics, fill factor will be affected, because fill factor we discussed, that is maximum area under the curve, that is maximum power divided by VOC into IOC. So let us now consider two things, ideal case and a curve with a high value of series resistance. You can observe how the fill factor will affect it. Say this is the IV curve for very small value of RS. You can say this is the maximum power point. Vm Im. So P max in that case will be Vm into Im. But suppose another case when RS is different. Curve looks like this. And in this case, if it is the maximum power point, this will be Vm dash, this will be Im dash. So P max dash will be Vm dash Im dash. So must, it is observed P max dash less than P max. But VOC and ISC product, that remains same. That means fill factor reduces with increasing RS. The ratio PM by VOC ISC, that fill factor indicates fill factor that will reduce. And the slope of this curve near this, if you take the slope here, delta I suppose by delta V, this gives you 1 by Rs, because delta I by delta V, so inverse of this slope Rs. So near the open circuit voltage point, this slope gives you the information about series resistance. So inverse of the slope is series resistance in this case. Which indicates that Rs affects the slope of the IV curve near the open circuit voltage. Now, what is the effect of shunt resistance? The shunt resistance provides a low resistance alternative path in the junction. Alternative path, that is a bypass path in the PN junction, to bypass the PN junction path. This leakage current reduces the total current available. So earlier we have seen the mainly voltage, the terminal voltage is affected due to presence of Rs, but here due to presence of alternative path, current, photocurrent will be affected. And ideal value of shunt resistance is infinite, which indicates there is no alternative path. Low resistive path means RSH is low. So ideally it should be infinite. Ideally there should not be any alternative path for photo carriers to flow. So if we have a RSH, effect of RSH on the curve, it mainly affects the current, and unlike the case of series resistance where the slope near the VOC is affected, in case of shunt resistance it is expected that the slope near the ISC, that will be affected, and ultimately that will also result in reduction of fill factor, but nature of curve will be different. Effect of RS is observed due to the change in slope here near the VOC, but let us see how in case of RSH it affects the curve. Here in this graph we have considered RS is 0, no effect of RS is considered, only effect of RSH. Similarly, in earlier graph, this graph, we considered that effect of shunt resistance is not there, only effect of series resistance is there. That means in this graph we have considered RSH is equal to infinity, and here we are considering RS almost equal to 0, only to see the effect of RSH. You see, for a infinite value of RSH, which is ideal case, the blue curve, which is following the ideal one. Now, if RSH reduces from the infinity, say 1000 ohm centimeter square, so red dash curve is shown, which mainly seen that the current is affected. So slope changes near the ISC, this point. Here the slope changes. if we take the slope here, this slope, the delta I by delta V, gives you the inverse of RSH. For an ideal case, for delta I and delta V, there is a no change in delta I. So for ideal case, this is infinity. For ideal case, delta I by delta V is almost equal to 0, which indicates RSH infinity. But here, delta I by delta V, it has finite value. So RSH is not equal to infinity. Similarly, for further lower value of RSH, say 500, the slope changes further near the ISC. So it mainly affects the slope of the IV curve near the short circuit current ISC or in JSC. Since the plot here is in density, same effect will be observed in case of current plot instead of current density plot. Now, what is the equivalent circuit including these two effects? First of all, we have an expectation that one resistance must be in series, which reduces the voltage, terminal voltage, and another resistance should be in parallel to the current source, which the current through that resistance will reduce the total current, net current at the terminal. So this was the case of ideal case, that is photocurrent minus dark current. But in addition to that, there will be some component like this, RS and RSH. This RS is in series as expected, and so potential drop across this RS, obviously from current is flowing, suppose from here to here, so this plus minus, this potential drop would reduce the terminal voltage here, this terminal voltage will be reduced due to this effect. And you see here the IL, that is the photocurrent, some is dark current, some is current through the shunt resistance. So we can write IL minus ID minus ISH. That is the net current. Terminal current. Also, this current will be drop, some potential drop will be across this RS. That drop will be RS into this. So potential drop across RS will be potential drop across RS into IL minus ID minus ISH. So the equation for the current voltage relationship will be like this. I is equal to IL minus ID minus ISH. But one thing you should remember, the terminal voltage V is here and the voltage across this diode, what is the value? So that will be V plus I into RS. Obviously, because if it is the terminal voltage V, so voltage appearing across this diode, that will be this V plus IS into RS. That amount of voltage is between these two terminals. So this between these two terminals, this voltage is V plus I into RS. That's why In the expression of current for the diode, that is exponential QV by KT, the QV is replaced by Q into V plus IRS by KT minus 1. And similarly, what is the current ISH? The voltage across this RSH divided by RSH. What is this voltage? This voltage is nothing but V plus IRSH. That's the expression. So these RS and RSH can be modeled in this way through equation and also through the equivalent circuit. But the problem is, if you observe this equation, I is equal to IL minus I0, this term, you observe that I, the current term I, is present in the form of exponential term in the right hand side. Also, I is present in the left hand side, here and here. Also, it is present here. But due to presence of exponential form and also presence of I in both right hand side and left hand side, you cannot solve this equation analytically, because this is a transcendental equation. So this can be solved only by iterative numerical methods, say Newton-Raphson method or other methods, say fixed point iteration method. What is iteration? You have to first guess a value of current I as an initial guess. You have to put the value of that I in the right hand side, and what is the value I you are obtaining, you observe. See the difference, what you assume the I and what you are obtaining the I. Now there is a big difference. So again, you put this value of I into this right hand side. Again, the extracted new or calculated I value will be different. So we have to reach in such a condition that whatever we are assuming I and putting in the right hand side, the same result should come in the I in the left hand side. That means if we assume, say, I is equal to 2 milliampere, after calculation in the right hand side, this I should come at also 3 milliampere. Then you can say this solution is okay. In this way, by initial guess and following some iteration, step by step, you have to reach the solution. These steps are written here. Start with an initial guess for I, substitute it into the right hand side, iterate until the difference between successive values. There is also technique. So I value, whatever you are obtaining here, and again you put this I value, those two successive I value you observe and take the difference. If two successive I values are differing by a very small amount, say 0.0001, this you can set this value, or say 0.01 as per your accuracy, then you have to stop, and that value of I, whatever you assumed or whatever is coming, this is the solution. So in this lecture we have discussed origin of series and shunt resistances, which is responsible for deviation of IV characteristics of a practical solar cell from its ideal counterpart. Due to presence of series resistance, mainly the terminal voltage is affected. Due to presence of shunt resistance, current is affected. Shunt resistance presence affect the slope near the short circuit current point in the curve, and presence of series resistance affects the slope of the curve near VOC point. Ultimately, in both the cases, fill factor will be reduced. Since fill factor is reduced, efficiency also reduced. So our intention will be always to reduce the shunt resistance and series resistance as much as possible. So we have to reduce as much as possible. That means we have to have a very low value of series resistance but very high value of shunt resistance. Shunt resistance ideal value is infinite. Series resistance ideal value is 0. In the equivalent circuit also we have shown including these two effects, these two resistances, and the equation for the relationship between I and V is transcendal equation if we include the values of RS and RSH, which can be solved by numerical iterative methods. And in the numerical simulation, what is the main motive of this course? That these can be solved easily by several techniques to get the final value. This reference book you can follow. Some other books also in the reference list we are mentioning in last few classes also you can follow. Thank you.